Hello everyone. So welcome to week 11's live interaction session for the Aspen plus simulation software, a basic course for the beginners. So as we have been doing this live interaction session from the start of the course, and this is the 11th session, and one more session we have to go. So that will complete the 12th live interaction session. Plus, I'm also planning one extra session where we will do some problems and have a quick recap of what we have learned in this course by so far. Okay, so just a brief about me. I'm Bhavesh Moorjani. I'm a TA for this live interaction session for this course. I have completed my bachelorates from MS University Vadodara, where I was introduced with the Aspen plus simulation software, and currently I'm pursuing my PhD from IIT Bombay. So if you have any query related to this course, you can contact me via my email ID or through my LinkedIn. Okay, so just a few announcement that I want to make before start of the class, that for the assignment 11 and 9 there have been some issues. So I have been in contact with Professor Saha, and I have tried to bring the issue to his notice. So one issue is that in assignment 11, for the given data, there is no reaction occurring. So I have informed the sir, and he has said to wait for a few days and then he will get back to me. So once he will approach me, I will update regarding the assignment 11 issue. Okay, so this was the question. Missing information for the PFR data as well as the feed condition I have already uploaded into this Q&A form. In the forum itself I have updated the details, if you will see here, and then there was again query that there is no reaction happening. So this detail, like this information I have passed on to the sir, and once he will respond, I will update it here. I had also tried to update it in this forum, but my message were not getting posted. They were getting deleted on its own when I was posting it. Same for many of the student has doubt on the assignment 9 part. Here also, for the given data, when we perform the simulation, we are not getting similar results as that has been provided into this Swayam portal. So for that also I have asked sir that if he can look into that. So once I get any update, I will inform you guys. Okay. Again, there was some issue in the posting this announcement in the Google group form. So I had tried to post it multiple times, but every time it was deleting my post for some reasons. So I don't know. So that's why I am starting this session by informing you that both of these queries I have put it forward. Once sir responds, I will let you know. Okay. So coming back to our course content, so we will start from where we had stopped last time. So last time at the end we were discussing this extraction column. So extraction by a series of decanter rather than a particular extraction column. We have series of decanters that has been placed one after the another, and the extraction process has been carried out. So in that case, how to solve this simulation, right? So first let me go into the basic theory, what we are going to do here. So here we have mixture of ethyl acetate and acetone, from which ethyl acetate has to be extracted via 3-stage extraction process, and our solvent is water in this case. So what is happening, that our feed is coming into decanter 1 where water is added. In decanter, due to the phase separation, we will have liquid liquid equilibria and phase separation will occur. We will have one extract phase, one raffinate phase. That raffinate phase is again transferred into D2 where we have water coming in. Again same, you will have extract and the raffinate phase. That will go to the third decanter D3, where again you have solvent coming in at all places. From there, last separation of extract and raffinate will happen. Okay, so this will be our final products. Okay, so we have to find how much separation can be achieved via this method. Okay, so for that, let's begin a problem. So this time I'm using, due to some of the licensing issue, I'm using my lab PC to run the Aspen Plus. So there might be some connectivity issue. If that happens, please bear with me for a few time. I will try to resolve it. Okay, within appropriate time. Yeah, as you can see, it takes a lot time to run it there. Anyway, so let's us start our simulation. So we have mixture of ethyl acetate, acetone and water as a solvent. So first we will add all the components. Ethyl acetate, then we have acetone, and lastly we have water as a solvent. So add that water, it will come last. Yeah. Okay, once all the components are added, we will select the property estimation method. So in this problem it has been provided that we have to use NRTL property method with the missing binary interaction parameter calculated via unifact method. So select NRTL, estimate missing parameter via unifact, and do the property analysis. Now in this problem statement, it has been said that ethyl acetate has to be extracted. Okay, from a feed which flow rate, whose flow rate is given as 1 kg per minute, with 70% ethyl acetate and 0.3% by weight acetone, and water is used as a solvent. All the feed as well as decanter are running at 25 degrees centigrade and 1 atmosphere. Now here, what do you think? What will be our solute? As in the what liquid will be our part of extract and what will be part of our raffinate. So obviously water should be the majority component of the extract, but with water, which component will get solubilized, ethyl acetate or acetone? And what will be the raffinate composition? Will it be rich in the ethyl acetate or acetone? So basically we want to see which component, either ethyl acetate or acetone, will have a more affinity towards the water. Right now we are not sure, although it has been said that ethyl acetate has to be separated, but will it be part of my extract or will it be part of my raffinate? I don't have an idea. So let's say ki acetone has more affinity towards the water, so that should come out in terms of my extract, which will be rich in the water and acetone, and my raffinate will be rich in the ethyl acetate part. If ethyl acetate has more affinity towards the water, then in extract I should have both ethyl acetate and water in majority component, and while my raffinate should have the acetone. Okay, so here we don't know it. So if you don't know it, in that case we can perform binary property analysis. So if you will recall, in our previous week's class we have done this property estimation and property analysis methods, okay, in the Aspen Plus. So go to the binary analysis. Now we want to see the solubility of both acetone and water as well as ethyl acetate and water. So for that, if you will recall, we had used this Gibbs energy of mixing. essentially it shows whether the mixing of your component will be possible or not, right? So what we will do at 25 degrees centigrade and 1 atmosphere, we will try to see which component has more affinity towards the water. So for that, component 1 is ethyl acetate, component 2 select it as water, mole fraction of ethyl acetate starting from 0 to 1, 50 interval points, and these are the temperature pressure condition. Run the analysis, and this is how this plot looks like. So as you can see, for a low fraction of ethyl acetate in water, the Gibbs free energy of your liquid mixture is positive. Since Gibbs free energy is positive, that shows that this mixture is not possible. At the higher concentration of ethyl acetate, we see Gibbs free energy is negative. That means some amount of water is soluble in the ethyl acetate, else you will see a distinct phase separation in terms of ethyl acetate and water. So water does not have much affinity towards ethyl acetate, that we can conclude. We can also look at the Gibbs free energy of acetone and water mixture. So here, yes.
Sir, free water pattern क्या होता है? What is a free water method?
Sorry, can you repeat it again?
That is a free water method.
Free,
Simulation में property method में दिखाता है, it show करता है free water method.
so free water method is essentially where you have water which is not part of any process fluid, but it's present in some amount. So it's not a major part of your process fluid or your reaction media, but it is present in some amount. So that's when you consider it as a free water, which is just there. Either it could be the byproduct of your some reaction or as an impurity. So in that cases, you select some of the method which are specifically designed considering the free water basis.
By default तो steam TA by default उसमें Aspen plus में होता है.
By
अगर
default,
change कर दे, हाँ sir.
sorry, can you repeat by default what?
Free water method में by default method steam TA यूज होता है. अगर आप अगर property method मॉड्यूल में जाओगे तो उसमें by default steam TA हो, पर SRK में steam NBS यूज होता है. तो अगर हम steam TA यूज करेंगे तो not आंसर एक्यूरेट नहीं है, तो कुछ एरर है.
That you have to verify. So I'm not sure about both of the methods which is used when. So maybe you can do some search on that, or you can take help of this. Oh, I haven't started my screen sharing, sorry. Anyway, no one was present here. Yeah. So
go to simulate property.
yeah, we are here only. So what method you are saying? Steam TA, right? Use this property method for pure water and steam. The Aspen physical property system uses steam TA as a default property method for the free water phase when free water calculations are performed. For the process calculation, the accuracy
property method पहले से include होता है. अगर SRK यूज करेंगे तो फिर not है possible.
If we will use SRK, then what? Then it will
Steam
use
NBS
steam NBS.
both.
Okay, just let me search steam.
लिखा है तो है. From some application ST nucleus can be that.
Is it steam NBS? ऐसे लिखा हुआ या uses same equation as steam NBS but with different root search, pure water and steam, and in particularly for free water phases, and the steam temperature range from 273.15 to 2000 Kelvin. The maximum pressure over is 10,000 bar. The steam NBS method is recommended use with SRK and okay. So it could be the way this property estimation method is designed. The parameter that has been optimized for this method works best with the SRK and this other method. So that could be the
free
reason.
water phase means free water phases मतलब सर उसमें water present नहीं होगा.
No, water will be there, but as I'm saying that so in many calculations you compute free water basis, like free water mole fractions if you have came across somewhere. So in that cases your water will act as an inert or some byproduct, not byproduct, but as an inert only, that it won't take a part in your reaction. So basically it's present there. So in that cases you will consider it as a free water. Okay. So if you will see, let's we search here. If you would have searched it, you might free water. Sorry, free water basis. Anyway, Aspen Plus have two approaches of modeling: the rigorous three-phase calculation with a free water approximation. When you use free water approximation, Aspen Plus assumes the free water phase is pure liquid water, so that's why free water. Free water calculations are normally adequate for water hydrocarbon system where hydrocarbon solubility in the water phase is generally negligible. So water will act inert in these applications, always faster than the rigorous three-phase calculations. Okay. So when you use free water or dirty water calculation,
इसलिए valid है या vapor phase के लिए valid है या liquid vapor phase के लिए भी ये VLA?
Yeah, it's valid for all, right? So the temperature range that was mentioned was from 273 to 2000 Kelvin, okay, until 10,000 bar. So it's valid for all phases, and water will kind of act as an inert, so it won't be taking part of your any reaction or in the process. So as you can see here, it's mentioned in the hydrocarbon application, right, that it will act as an inert. No hydrocarbon is soluble in the water, so that's why water will be treated as a separate phase. So it's kind of to ease the calculations, to avoid the complications. Okay, that's the whole purpose. I hope it answers your question. Okay. Then I will move ahead with the problem. So we had seen the Gibbs energy of mixing for ethyl acetate and water. Now we want to see acetone and water. So select acetone, then water. Again at 1 atmosphere and 25 degrees centigrade we will see the Gibbs free energy of mixing. So you can see here the first plot, this was for ethyl acetate and water mixture, where you can see much portion for the much composition Gibbs free energy is positive, showing no mixing is possible, while for the complete range of acetone and water you can see Gibbs free energy is negative, indicating that mixing is possible. So in this case, in our problem statement, what will happen when we will add water, acetone having an affinity towards the water will get out with the water. So in the extract, what should we get? Water as well as acetone, and in the raffinate it should be rich in the ethyl acetate part. Okay, and the final product, so we have been asked to separate the ethyl acetate, so that will be present in the final raffinate. So let's now go to the simulations. Once we have figured out what are the extract and raffinate phase, we have to add 3 decanters in a series. So we have decanter 1, decanter 2 and decanter 3. Let's connect them. So feed is coming here, then this is first liquid, so let's connect it to the feed. Then we have secondary liquid, which should be our extract 1. Raffinate of second decanter will go to the third. Extract 2. Raffinate of third decanter. Extract of third decanter. In every decanter, water is coming, so we will add water stream for all. So now let's just rearrange it first for a better representation. Let's name it as W1. This will be W2. Then W3. This is our feed, so feed F. Okay, let's call this as extract, so this is extract E1. This is our raffinate R1. I'm just rearranging it for a better representation, nothing else. From the second decanter we will have extract 2 and then raffinate 2. Then from the last decanter we will have E3 and R3. Okay, now specifying composition feed data. So first, for the feed we have a flow rate of 1 kg per minute of ethyl acetate and acetone mixture with 78% of ethyl acetate. Feed is coming at 25 degrees centigrade and 1 atmosphere. 25 degrees centigrade, 1 atmosphere. Flow rate is, mass flow rate has been provided. One kg per second, sorry, kg per minute. Yeah, 1 kg per minute with 70% ethyl acetate and rest is acetone. These are the mass fraction. Okay, so select mass fractions, go next. Sorry, go next. Now we have to provide the details of water. So water is entering at each stage with a flow rate of 1 kg per minute of water, which is entering at each stage. And again the feed conditions are same as 25 degrees centigrade and 1 atmosphere. So water will be 25 degrees centigrade, 1 atmosphere. We will provide mass flow in kg per minute for water is 1. Okay, same we have to provide for other decanters entrance also. Mass flow rate kg per minute, which is 1. Okay, and the temperature pressure condition for each of them is same. Now this key component to identify second liquid. So second liquid here we have provided, so we are referring it as an extract. So in the extract, what should be the major component? Water. Being a solvent, it should be the key component. Okay, so provide that.
क्वेश्चन
Yes.
सर कोई सब्सटेंस सर इनर्ट है तो रिएक्शन में पार्ट करता है कि नहीं करता?
No, inert won't take part in the reaction.
फिर सर इनर्ट को डाला क्यों जाता है? मतलब वो सब्सटेंस को एक इनर्ट
Why? So why inert
क्या
is
करें?
being added? That's what you are saying. If it's not taking part in reaction.
उस
So in many times, separation of component becomes much costlier. So if you have inert present in your system,
सॉलिडिटी
sorry,
सॉलिडिटी के लिए करते हैं सर इनर्ट यूज डेंसिटी की वो ऐड
actually,
करते
actually your voice is not clear to me. What you are saying? Can you speak it slightly loudly?
सर ये क्या है कि मैं या डेंसिटी इंक्रीज करने
किसके लिए यूज करते हैं?
सॉलिडिटी के लिए
Solubility. No, so no, the reason for inert is again, so separation might become difficult or it's costly, and since it's inert, you keep it there. I mean, there is no point of separating unless it's absolutely necessary. That's why inert is being present. In the hydrocarbon application also, it's, I mean, for hydrocarbon and water mixture, obviously water can be easily separated due to with the density itself.
कोई किसी हम उसमें डाल रहे बैच में डाल रहे रिएक्टर पे
हाँ.
तो हम वो करते कभी कब करते हैं रिएक्शन की
No,
सपोज करो टॉल
so from what point you are looking at? From a solubility point of view, from a reaction point of view? So both, with both perspective, your answer will be different, right? So for a reaction, it might be to control the composition part. That okay.
सर पॉइंट ऑफ व्यू रिएक्शन
So from
की रिएक्ट
हाँ. So from point of view of reaction, to control the composition, you might add an inert component, right? So it will depend upon your reaction kinetics, how much conversion you want to achieve. Another thing
सर वो
could
रिएक्शन
be, yes,
रिएक्शन में वो कोई हेल्प भी नहीं कर रहा ना इंक्लूड हो रहा है तो फिर भाई
yeah, that's what
ड्यूटी
I'm
क्यों
saying.
करते हैं?
So I don't have a perfect example right now, but there are some reactions where you have to maintain a composition of your feed to some optimum range in order to get a maximum conversion. In such cases, you add an inert. There are some places, so that could be the one reason. Second reason could be, which I was saying initially, that inert, it might be difficult to separate the inert. It might become a costly thing. So in that case, you don't bother about separating the inert. Since it's an inert, let's say nitrogen and oxygen, air mixture, okay? So you have oxygen, nitrogen, some argon and some smaller components present. In that case, nitrogen, if it's not taking part in the reaction, why to separate nitrogen and oxygen? It will add to your cost, right? So that's why you don't separate it. So that are the reasons. So that could be the second reason, that separation cost will be too much, so there is no point of separating it. uh, and what else could be there? Yeah, so I think these two are the prior like major reasons why inert is being present. Yeah, a third reason could be this also, that to control the heat of reaction. So if your heat of reaction is more, then if inerts are present in your system, then they might absorb the heat, and your reaction temperature or the reactor itself is maintained at some optimum temperature. So that could also be the reason. So there are multiple reasons why inert is there.
Point of view of solubility.
No, solubility is not there. I don't
Separation के
know.
साथ
Like, are you talking about specific example?
सेपरेशन पे कर सकते हैं सर इनरटली.
क्या कर सकते हैं
सेपरेशन के लिए सर.
सेपरेशन के लिए?
डिस्टिलेशन के सर.
Distillation and inert doesn't have any relation as such. I'm not sure about that. Let me think if something comes in my mind. Okay. But for distillation, it should. No. No, for distillation, I don't think so. There is a role of inert there. Okay. Anything else? No? Okay. So we will continue. So add water as a key component in all the decanters. Pressure temperature conditions are same for all of them. Okay. So once added, just run the simulation. Results are available, and there are no errors. So first let's see what is happening in the decanter 1. So in the decanter 1, we had our feed coming in, water coming in with a mass flow rate of this. So kg per minute. Yeah. Okay, so this was the mass flow rate. Water was being added as a solvent. So in our extract, as we had discussed, that major component will be water. Along with water and acetone has a good solubility compared to water, and like acetone has a good affinity towards the water compared to the ethyl acetate. So in the extract part E1, we should have more amount of acetone compared to ethyl acetate, that is being there. And in our raffinate, majority component should be ethyl acetate, then acetone, and followed by the water. So that is the case, right? Similarly, for the decanter 2 output, if you will see, same thing is happening, that we have 0.597 kg per minute ethyl acetate coming in, that is out of which 0.500 ethyl acetate is present in the raffinate. 0.12 from 0.12 kg per minute of acetone, only 0.04 kg per minute acetone is going into the raffinate. So ethyl acetate is being separated in the raffinate part, while in the extract part water and acetone is going. Okay. And at the end, last output of decanter 3, which will be our main product, so R3, and combine E1, E2, E3 are our products, right? And we want to separate ethyl acetate. So R3 whatever amount of R3 is present in the ethyl acetate, that will be our separation. So we had achieved total separation of ethyl acetate as sorry, this is kilomole, these are molar fraction, yeah, here. So from 0.7 kg per minute in the feed, we have separated 0.415 kg per minute of ethyl acetate in the raffinate. So this is how the separation of ethyl acetate is achieved. But here we have not used any extraction column, rather extraction followed by series of with the help of series of decanter is used. And in a way, if you can assume, this will act as a extraction column with three stages of the three different stages, okay, where solvent is introduced at each stage, right? Now some of the question that has been asked to us: mass fraction of ethyl acetate obtained out of the second stage in the ethyl acetate rich phase. So second stage is this B2. Let's check our result whether they are matching or not. For the B2 part, if you will see the stream results, we have been asked to find the mass fractions of ethyl acetate in ethyl acetate rich phase. So that is our raffinate. So mass fraction is 0.87. Is that the case? Yeah, so our answer in the range. Heat duty of the second stage. So for the second stage, heat duty in kilowatt, it's minus 0.258. Again, that we are in the range. Heat duty for the third stage, you can check that also. Which is minus 0.164 kilowatt. Then it has been asked temperature of the feed entering the third decanter, so that we know everything is operating at 25 degrees centigrade. So they have just asked it in the degree Fahrenheit. The overall percentage recovery of ethyl acetate, how much percentage recovery of ethyl acetate has happened. So for that, we know we have the mass flow rate of ethyl acetate. So it has not been provided, so we will look from the mass flow rate only. So we had 0.7 kg per minute ethyl acetate coming in the feed, out of which we extracted 0.415, that divided by 0.7, so around 59.3% recovery we are obtaining. Okay, so that should be your answer. So this was the example 1 for today's class. Now we will move forward with the second example. This is also again related to the separation, where we have stream containing 50-50 weight percent mixture of water and acetone with a flow rate of 150 kg per hour at 25 degrees centigrade and 1 atmosphere, which is mixed with ethyl isopropyl ketone EIPK flowing at 75 kg per hour flow rate, again at same condition 25 degrees centigrade and 1 atmosphere, to form a ternary mixture product stream, which is fed into flash tank. From flash tank we will get two liquid output stream are separated. Property method is NRTL that we have to use. The second liquid which is coming out of the flash tank is mixed with another identical feed of EIPK to form a secondary ternary mixture, which is fed into the another flash tank at 15 degrees centigrade 1 atmosphere. Again from the second flash column, the first liquid outlet stream of the two flash tank separators are then mixed and fed into the red flag column on above stage number 5. Column operates at equilibrium and the column data is given. So the maximum number of iteration for third mixture is 60 degrees centigrade. The column has 10 stages with phases: vapor, liquid, water, condensate. The condensate type is total, distillate to feed ratio is given, molar reflux ratio is given. Now the feed basis is mixed feed that is fed into the column. Component is acetone. Condenser pressure is also given. So carry out design specification study to achieve the mass fraction of water of second liquid stream coming out of the second flash as 0.85. Okay, so quite of the data is given, but overall what is happening here is that we have one feed. Let me show you. So we have feed.
जो आप सिमुलेशन कर रहे हो स्टडी स्टेट सिमुलेशन है डायनेमिक?
Sorry, what you are saying?
So ये स्टडी स्टेट डायनेमिक सिमुलेशन है या डायनेमिक?
In a way you can call it as a steady state. So like at equilibrium your all composition and things won't change, right? Dynamic simulation will be where your things are continuously changing with time. So like for a reaction you can consider it as a dynamic part. Okay, I mean like this is not the exact term to define a steady state and dynamic. So dynamic we will use when there are changes occurring with time. Okay, so here once the equilibrium is achieved, the composition at the feed inlet, composition at the product outlet, that will remain same. So that steady state is achieved. Dynamic will come when you have feed composition changing with time, then your product composition is changing, or your pressure fluctuations are there in the system, then it will become dynamic. So currently all the simulations that we are doing, so we are considering steady state. Okay, but in actuality there might be some changes. Let's say in your distillation column pressure fluctuation might happen, so that will become a dynamic part. So accordingly your feed composition will change, sort of a thing, right?
सर डायनेमिक पोर्शन कब कराएंगे?
Dynamic portion is not part of this course. It's a basic course. So in some advanced course you might learn the dynamic part, and in the dynamic part basically you will learn about including controls in this various process models that we have learned. Okay,
दूसरे साइड तो कंट्रोल वॉल्व करा रहे हैं, उन्हें डायनेमिक वाला करा रहे हैं.
sorry,
जो दूसरे सर है ना सर, उनका नाम क्या है? राकेश.
okay.
ने एग्जांपल दिया था डायनेमिक का.
Oh, so you are saying that another TA or some other professors?
Yes sir, another TA.
Another TA.
आपकी तरह.
Okay. Rajdeep, I think his name is Rajdeep.
Yes sir.
Yeah.
कल ही करे थे सर.
Okay, it could be. So in the last lecture, so in the week 12 part of this Swayam course, Professor Saha will introduce you some of the dynamic parts where simulation with some control example will be given. So probably in next lecture I will also try to cover some aspect, but basically what we have done so far and the majority of this course is related to steady state and not the dynamic part. So coming back to our problem, so we have feed which is separated in the flash tank. Okay, from flash tank we get two liquids. The second liquid is again fed into the another flash column. At the both entrance of the flash 1 and flash 2, EIPK, which is our solvent, is added. Again you get a two liquid product. Liquid product from first and second column, the top liquid product is fed to your distillation column, which is modeled using red flag column. So this is how the overall concept of this problem goes, and then we have to design it based on for a specific for a 0.85% recovery of mass fraction of water and of the second liquid coming out of the second flash. Okay, so this is how this problem statement goes. Let's try to simulate it. Okay. So we will add our component. So we have water and acetone mixture. Water acetone, and then we have this EIPK, ethyl isopropyl ketone. Let's see if its short form is present or not.
3 वाटर कंडेंसर मतलब
Sorry,
3 वाटर कंडेंसर क्वेश्चन में लिखा है.
हाँ,
3 वाटर कंडेंसर.
yeah, we will come to that part also. Okay, yeah, we will come to that part. Okay, so I cannot find EIPK directly, so let's write it's ethyl isopropyl ketone. Okay, so we have this. Okay, so that has been added. Property methods, we have to select NRTL. Estimate binary parameter by unifact method. After doing so, okay, here also you can look at the binary analysis and see which component has affinity towards each other. So we will again look at the Gibbs free energy, then we will look at water and EIPK Gibbs free energy. So as you can see, for most of the range, water and EIPK are not mixing. So they will two phases will be separated out. One will be rich in water, another will be rich in the EIPK. If you will see acetone and EIPK, that gives free energy is negative. So essentially EIPK is added to get to separate the acetone via since acetone and EIPK has a good solubility in each other, right? Now let's go to the simulation environment. So we have separators. Since we have LLE, like two liquid phases are being separated from the flash, we will use flash 3. Okay, we have two flash 3 in the series. Then after that we have red flag column. How they are connected? So our feed is coming, going into flash. MIPK is also coming, EIPK is also coming and it's going into the flash. From flash we will have water outlet, product 1, first liquid which will go to the feed in the red flag column, second liquid outlet which will go to second flash. Rather than directly entering them, let's put a mixture here and then add them. So what I will do, I will add a mixture. From a mixture, let me reconnect this line, reconnect to destination. So this is how it looks like. Let's do slight rearrangement.
अगर सर हम डायनेमिक सिस्टम ले तो सर वो अचीव तो करेगा ना स्टडी स्टेट.
Yeah, so dynamic, just a minute.
एक का रियल मॉडल ले, मतलब रियल प्लांट मॉडल ले, अगर कोई वर्क कर रहा है तो वो स्टेडी स्टेट में तो बाद में अचीव भी करेगा,
हाँ,
इक्विलिब्रियम तो आएगा।
yes, that's what I'm saying.
आइडियली
Your system will become dynamic when there are sudden changes that are happening and then you are tracing them. Else, any process plant, once the steady state is achieved, like, so let's say you have started one plant, okay, from you are doing a, after shutdown you are starting up the plant again, okay. So initially there will be so many things fluctuating, pressure, temperature of various streams, as well as composition. But once that steady state is achieved, so once the, like, all the temperature pressures are at their equilibrium value, then you can say the steady state is achieved. Even in that steady state, that doesn't mean that your pressure value or temperature will be a, you know, kind of a constant line. It will fluctuate somewhere around its mean, but still it will be some new steady state where you can see that the fluctuations are within the range, so you can consider it as a new steady state. So anyway, your dynamic system will at the end eventually should go down to the steady state. That is the overall idea, right? So if you want, I will look into some examples. If I can incorporate some of the example for the dynamic simulation, that we will try to do it. Okay. Yeah. So now since we have added all the details, let's just rewrite here. So this is our feed. We have solvent 1, so I am saying it as 1. We will have solvent coming in the second flash also. So let's call it as S2, solvent 2. From flash we will have vapor 1. This is liquid, let's call it as liquid from flash 1. So sorry, L2F1. This is first liquid from flash 1. You can use any convention. I am using currently just to differentiate them. This is first liquid from flash 2, second liquid from flash 2. This is our mixed stream M, and from the red frag I am selecting this liquid distillate since we know we have total condenser. Okay. So finally we will have our top product and we will have our distillate and this. Now let's add the details. So 50-50 weight percent mixture of water and acetone with a flow rate of 150 kg per hour at 25 degree centigrade and 1 atmosphere. So temperature is 25 degree centigrade, pressure is 1 atmosphere, mass fraction is provided as 0.5 for acetone, 0.5 for water, and flow rate is 150 kg per hour.
सर फ्लोट फ्लो के लिए एस्पेन प्लस यूज कर सकते हैं ना?
अगेन फिर से बोलिए।
सर फ्लोट फ्लो है ना, उसके लिए एस्पेन प्लस यूज कर सकते हैं।
फ्लूइड फ्लो में, बट बेसिक व्हाट यू वांट टू सिमुलेट दैट?
मोमेंटम।
आई डोंट थिंक सो। फ्लूइड फेज, फ्लूइड डायनेमिक्स के लिए उसके अलग सॉफ्टवेयर आते हैं, कॉमसोल एंड आई थिंक ओपन फॉर्म या समथिंग, तो वो अलग सॉफ्टवेयर है इफ यू स्पेसिफिकली वांट टू स्टडी फ्लूइड डायनेमिक्स।
एस्पेन फ्लुएंट तो है ना सर, वो भी तो यूज होता है।
विच सॉफ्टवेयर?
एस्पेन फ्लुएंट, FLUENT।
ओके, आस्पेन का ही है या तो दैट कुड बी, या बट आस्पेन प्लस इज स्पेसिफिकली फॉर प्रोसेस डिजाइन, नॉट द फ्लूइड डायनेमिक्स पार्ट। उसके लिए दूसरे आइदर आस्पेन में ही, इफ यू आर सेइंग दैट इज अ सॉफ्टवेयर, or else there are other softwares also that has been that are being used to see the fluid dynamics. COMSOL is also there, people use that. Yeah, so we had added the feed details. Now EIPK. So EIPK is flowing at 75 kg per hour and at the same condition. So we have two EIPK stream, solvent 1, S1. So let's add it here. We have mass flow rate 75 kg, 25 degree centigrade and 1 atmosphere, right? Same for solvent number 2, which is at 25 degree centigrade, 1 atmosphere, 75 kg per hour. Now we have to provide the details of this flash. So for that, what has been mentioned to us, they are fed into the flash tank, which operates at first flash is operating at 10 degree centigrade and 1 atmosphere. From there, two liquid output streams are separated. The second liquid coming out of the flash tank is mixed with the another identical feed stream of EIPK to form a three-phase mixture, ternary mixture, which is fed into the second flash tank at 15 degree centigrade and 1 atmosphere. So first tank is operating at 10 degree centigrade, 1 atmosphere, B1. B2 is operating at 15 degree centigrade, 1 atmosphere. Then the two first liquid outlet stream of two flash tanks separated are mixed and fed into the red flag column at stage number 5. So now we will add the data for red flag column, which is B3. So in that column has total 10 number of stages, 10 number of stages. Condenser type is total. Okay, you can see here the column has 10 stages. Now it has been provided that we have vapor liquid free water condenser. Okay, so now we want to see what does it mean. So essentially when we say as we were discussing earlier also, that free water in a way it will be third phase. So here we have vapor liquid equilibrium, but the third phase which has a more amount of water, it can be treated as a separate phase, so it doesn't have any equilibrium with the phase 1. So as you can see, we have mixture of acetone and EIPK, out of which EIPK and water does not have any negative gives free energy values, right? So their mixing is not possible. So in that case, what will happen, your secondary phase, which will be water, it will be kind of a inert only. So we don't have to, instead of taking it as vapor liquid having to do compute the liquid equilibrium, we can look at the select vapor liquid free water condensate. Okay, so that's why it's being selected here. So it's essentially to make the computational less expensive. That's it, like to ease out the calculation that we are doing. And then what other details we have? Distillate to feed ratio is given as 1. Reflux ratio is given as 6. Okay. Now there is one more thing that has been provided. So it has been said that the reflux ratio, the feed basis is mixed feed that is fed into the column. So here you can see you have feed bases. So feed basis is mixed, which is a mixture that has been provided to the column now, and the component is acetone. Now what does it mean? So if we are not sure, we will take the help here. So it has been mentioned that feed basis for distillate bottom ratio specification. Till now we haven't bothered about the the basis that we provide, distillate to feed ratio or reflux ratio. Is it related to overall distillate to feed flow rate, or is it to specific component? But when we have provided the basis, so here it is mentioned that feed basis for distillate to bottom ratio specification. So this point, this ratio of 1 distillate to feed will be considered for the acetone, okay, rather than looking at the total distillate to feed ratio. It will look at the flow rate of acetone in the distillate and flow rate of acetone in the feed and consider that. Now next other details that we have to provide, that this mixture is entering at above stage number 5, as has been mentioned in the problem statement. The column is operating at equilibrium. The maximum number of iteration for third mixture is 60. That is for mixture, so that we will come again for that also. Pressure value, the component, the condenser pressure at stage 1 is 0.5 atmosphere. So condenser is operating at 0.5 atmosphere. Another detail that has been provided is the number of iteration in the mixer. Now I am not sure why this detail is provided. It could be the problem statement that the book that I have referred, it might not have converged within the 30 number of stages, so that's why. Okay, you can try it out with this lower number of iteration and see whether it's working or not. Now we have completed our flow sheet. We can run the simulation and see what is happening here. So we have our results available. So let's look at the first the flash drum B1 and B2, what is happening there. So for the first flash drum, you can see we don't have any vapor product. We have two liquid phases being separated. Since we are operating at fairly low temperature of 25 degrees centigrade and 1 atmosphere, this was expected. Now in the molar flow rate, what we see that our first liquid coming out of the flash 1 is mainly constituting EIPK and acetone. We had seen that EIPK and acetone had a good affinity compared to EIPK and water. So in the first liquid, water amount is much less compared to what we have in the feed. And the second liquid mainly contains water, some amount of acetone and EIPK. This is then fed into the second flash column. In the second flash column, again this acetone is being removed by EIPK. So the first liquid will contain EIPK, acetone and some amount of water, while the second column will contain mainly water. So from both flash 1 and flash 2, the bottom product was mainly containing the liquid. Now the top product, which had EIPK, top liquid from flash 1 and flash 2, which had majority of EIPK and acetone with some amount of water, is mixed and fed to our distillation column, where separation of EIPK and acetone should happen. So for that, if you will go into the stream summary for the column, distillation column, what we see here, the molar flow rate is given. Now you can see we had seen in the flash also, when we had three components, it was separating out in the three phases. But since the water amount is less, and we have selected the method as vapor liquid free water basis, free water condensate basis. So instead of using vapor liquid equilibria, it will use some other property methods to ease out the calculation, to ease out the liquid equilibria part. Okay, and you can see in our distillate majority of acetone has come out with a small amount of EIPK and water, while in the bottom we have majority of EIPK and the remaining water. So this is how the separation is achieved for the water acetone mixture via third component EIPK, and that is being separated in the last distillation column. From here the raffinate, since it contains mainly EIPK, since the the bottom product of the distillate contains mainly EIPK, this can be recycled back again as a solvent also. Now, what extra thing has been asked here is that carry out a design specification study to achieve the mass fraction of water of second liquid stream coming out of second flash separated as 0.85, mass fraction of second liquid coming out of the second flash separator as 0.85 with a tolerance of 0.002, and we have to vary the flow rate of second EIPK stream between 50 to 300 kg per hour. So first let's examine what is the current flow rate that we have, current mass fraction that we have in the second flash. So for the second flash, mass fraction of water coming into the bottom product is 0.755, and we have been asked to increase it to 0.85. Okay, so let's carry out the design specification. For that we can go, either we can select design specification from this left hand side panel, from the left hand side panel also, or we can use this design specification block. And the design specification block, let's add the variable. So variable is water fraction, okay, that is stream variable, and we want to see the mass fraction of stream, second stream coming out of the flash 2, that too we want to look for the water. Okay, variable 1, sorry, I forgot to add it here. So water fraction is added. Now we will provide its value. Okay, so put water fraction in our specification column. We want its value as 0.85 with a tolerance of 0.0002. Yeah, sorry, 0.002, and we have to vary the feed rate of second MIBK that we are adding, so that will become a stream variable. Let's see, mass flow of solvent 2 that we are adding into flash 2. We have only EIPK. It should be stream variable also. Yeah, sorry, stream variable S2, and here we want to change its mass flow rate. the limit, the bound that has been provided to us is from 50 to 300 kg per hour. So lower bound is 50, upper bound is 300 kg per hour. Step size we don't have to worry about since it's an optional thing. And let's run the simulation. Results are generated. So let's find it out. So we had provided it 75. At 75, mass fraction of water was 0.755. But if we increase the flow up to 221, we will get 0.84 mass fraction of water in the secondary stream. Okay. Then what does it mean? It does this indicates that in the flash tube we want to extract out maximum amount of water in the bottom, in the secondary liquid, so that we have less amount of water present in our distillation column. So if you will see the stream results, the mass fraction of 0.85 is achieved, while the mass flow is 65. Only 4 kg per hour is going into the top liquid. Then our distillation column specification will also change. Here previously we had seen that, okay, we hadn't looked at the mass flow, but we were looking at the mole fraction. But that also has gone down in both distillation as well as if you will see in the bottom product. So majority of EIPK is in the bottom product with very little amount of water compared to the previous, since we have separated out majority amount in the second flash only. So this was the separation of again two components by adding third solvent. So both example 1 and 2 were kind of a part of in a category you can add it as an extractive distillation type. Okay. Now some of the questions that has been asked in the this part is the heat duty of the second flash separator. So that we can quickly look at and then can move forward with the second example. So for block B2, our heat duty in kilowatt is 1.056. Yeah. The vapor of liquid flow ratio, the vapor to liquid flow ratio for stage number 5 is asked. So for a distillation column, if you will see the profiles, in the profile itself, composition and the key values. Here. So on stage number 5, this is the stage number 5, we have been asked vapor to liquid flow ratio, mole basis. Okay, so this is the mole basis. We have vapor flow rate as 6.8 and then liquid flow rate as 10.8. So 6.8 divided by 10.8, you should get it as 0.629. Okay, so that our answer is matching. The vapor flow of stage number 6. So for stage number 6, vapor flow rate is at 7.68 kilomole per hour. Right, it's asked in kg. So for that you can change basis from mole to mass. Then your value will change. We have 355 kg per hour flow rate on the vapor flow rate in stage number 6. The mass fraction of acetone in the vapor phase in the 7th stage. So for the mass fraction, you can look into the composition value. Mass fraction of acetone at what stage? 7. Stage number 7 is asked. So that is 0.09. Again this is for vapor, we are looking at liquid. So for vapor, 0.28, 0.281, that is also there. Mass flow rate of second EIPK feed stream for a design specification, so that we found as 222, right? So we started with the 75 and we got at 221 kg per hour, we should get the desired value. So that this is the range of your answer. Now moving forward with the third example. So this is the example this is again a process plant simulation part, where this is an ammonia synthesis process that has been designed. So we will look into that. Meanwhile, okay, so I think Nikhil went away, and then there was some other student. Anyway, so we will look at the third problem. Just give me a minute. I think no one is here. Screen is being shared. Recording is also on there. Okay. So this was the second example. Now let's move forward with the third example. No, I don't want to save it. Yeah. So for this ammonia synthesis process, we have been said that we have an inlet stream H, which is coming at 80 degree Fahrenheit and 300 psi absolute pressure, which is compressed to 4000 psi absolute pressure using compressor B1. The flow rates for the stream H as provided. This process, ammonia synthesis process, is taken from the following reference, although I have taken it from another book, but they have cited this. Okay. Now this is the overall flow sheet diagram, where our feed is compressed, which is mixed with the recycle stream. Mixed stream is heated to some desired reaction temperature, then fed into the reactor, where our ammonia synthesis reaction happens, which is further cooled down and then separated into the flash column. From there, the top vapors are recycled, like some part is purged and majority of them is recycled back. Okay, so this is the overall idea of ammonia synthesis process. Let's read the details also. This stream F1 is mixed with the recycle stream in the block B2, which is operating at 4000 psi. Before entering into the reaction, the mixer effluent in this block are heated at 1900 degree Fahrenheit. Note that the reactor, which is R Gibbs, is operating at the 900 degree Fahrenheit and 3970 psi absolute pressure. The reactor outlet is cooled down to 80 degree Fahrenheit. Then it is flashed into the flash 2 column, where the vapor product of the flash is splitted. 0.01% of that part is purged, while rest is recycled. Before recycling, it is compressed back again to 4000 psi pressure value. Now we have to use NRTL thermodynamic model, Newton's iteration method, to simulate this ammonia process. Okay, and then compute the component wise flow rates and composition. Also, it has been asked to do a heat integration analysis to save the net utility of the process and how much energy we can save through heat integration. So we will look into this aspect also. First, let's add all of the components. So we have nitrogen, hydrogen, ammonia and carbon dioxide, which is acting as inert in this case, so CO2. Method. For method, we have been asked to use NRTL, and we have to use Newton iteration method. So for that we can change via data browser, choosing conversion options. Okay, so let's look into that. First, select the NRTL method, go go next. We will also select the conversion method as Newton. So for that we have to go to conversion/conv options, data browser. It should be here. Oh sorry, this will come in, this conversion part will come in the simulation part, not here, my mistake. So let's run the simulation. Property analysis is done. Now let's go into the simulation part. Here we should be able to select the conversion part. So in the conversion we have conversion options. There are various defaults method. So in that you will find in the tier we have to select the Newton's method as has been provided in the specification. So again this is just to illustrate that there are various parameters that you can change to optimize your process data, optimize your simulation data. Okay, so each method has some advantages, disadvantage. There is no particular reason that has been provided here, but it is just to give you an idea. Okay, that so within this various process equations that has been used, there are various methods for conversions also, and you can select one method, which is you can select out of that also various method that may or may not affect your simulation results. Okay, since we have selected this, now let's get back to our problem again, and we will simulate this complete ammonia synthesis part. So instead of going into piecewise operation, we will completely draw a process flow sheet, and then at the end we will try to optimize it, and we'll look at the heat exchanger aspect also. So feed, which is coming and being compressed, is then mixed into a mixture. From mixture, stream is heated, it goes to a heat exchanger. From heat exchanger we have a reactor. Reactor outlet is cooled down, so for that again we will use a exchanger. Now from the exchanger we have a flash 2 column where the separation process takes place. So flash 2, top product of the flash 2, it will be splitted into two parts. One will be purged and one will be recycled back. Before recycling back, the vapor outlet will be compressed to again desired reaction pressure values. Okay. So now let me reconnect all of them. So this is how our process flow diagram looks like. It's same as that has been provided into the problem statement. Now let's just rewrite them just to match the convention. So we have H, F1, F2, F3, 4, 5, 6, 7, 8. Okay, and then this is B. Okay. H, F1, F2, F3, F4, F5, F5, F6, this is 7, and last is F8. This is our purge stream, so I will call it as purge. This is our liquid product, so I will call it as L1. Okay, so this is how the convention is done. Now let's go and provide the details of all of them. So first, feed H. For that we have information that feed is coming at a flow rate of 100, 300 and 1 pound mole per hour of nitrogen, hydrogen and CO2 respectively. So molar flow rate, select pound mole per hour. So we have 100 nitrogen against 300 hydrogen, 1 pound mole per hour CO2, which is coming at 80 degree Fahrenheit and 300 psi. So 80 degree Fahrenheit, 300 psi A. Okay, this we can write it as 0 and this goes to our block B1, which is a compressor. So for compressor no information is provided, so we will select an isentropic compressor with a discharge pressure of 4000 psi, absolute psi, that has been mentioned in the problem. Then we have our heater. So heater will heat the feed mixture at 19 degree Fahrenheit with a 0 pressure drop. Okay, so outlet of heater is at 19 degree Fahrenheit. We can write it 0 psi, so 0 pressure drop will be considered. Then we have reactor data. For the reactor, it has been said that the reactor B4 runs at 19 degree Fahrenheit, but there is slight pressure drop in the reactor. So instead of 4000 psi, it's operating at 3970 psi. So reactor pressure is 3970 psi A, and it's operating at 900 degree Fahrenheit. Okay, now since it's a our Gibbs reactor, it will use the Gibbs free energy to compute the equilibrium conversion, so we don't have to provide a reaction here. Okay, if you will again recall all the reactor models that we have done so far, so these 3 models that do not need a kinetic data, our Gibbs does not need a reaction part. Okay, now what other information we have to provide is from there the reactor outlet is cooled to 80 degree Fahrenheit and at 3970 pressure. So again 0 pressure drop in the heat exchanger. Okay. The flash drum is operating at 80 degree Fahrenheit and 3970. So same condition for the flash drum also. Then the splits fraction. So for purge, it has been provided at 0.01. So 0.0001. This will be absolute value. Okay. So this much amount is purged while rest is recycled. So almost everything we are recycling back. That is being compressed. So compressor type, again we will select isentropic since nothing is provided, and it is again compressing back this recycled gas at 4000 psi A, right? And with that we have almost provided all the information. So now let's run the simulation and observe what are the values that are coming. So no warnings were issued and our simulation is complete. So we can directly look at the output of the flash drum, which is our main target. First, let's see B6 output. Or let's first let's look at the reaction part, then we will move ahead. So in the reactor, we have 61, it's kilomole, so let's change it to pound mole again. Pound mole per hour. Okay. So in our feed we had 100 pound mole per hour nitrogen flow rate, 35 came from the recycling, out of which from 135 conversion of around 99 happened. 99 pound mole per hour got converted to ammonia. As you can see here also, that 256 minus 58, 198 nitrogen, and for one, so this is the amount of our nitrogen. CO2 is acting as the inert. From here, the flash drum, which is our B6, separated it into two parts. One is vapor and another is liquid phase. In the vapor phase, which is F6, majority of nitrogen, hydrogen and some amount of ammonia out of 116, 26 kilomole per hour went into the vapor product, while rest went into the liquid. So majority of ammonia is in the liquid phase. So our liquid, flash drum liquid, is nothing but our main product, which is ammonia, while rest is being purged. Okay, just a moment. Here I want to check I have provided valid phases or not. Include vapor phase. You can provide CO2 as a non-reacting phase, but since its amount is anyway, it's not taking part in any reaction here. Okay. So as we had discussed, again, like our Gibbs will use a Gibbs free energy calculation to find the equilibrium composition, while for the CSTR PFR R batch we need a kinetic parameter. Similarly for our yield and equilibrium we need to provide some reaction part or some composition that we have to get, while this calculates the conversion based on the Gibbs free energy data. Okay. Now another thing, if you will see here, let's add the temperature, pressure and vapor fraction values. So you can see from let me change it to English unit. So this is back in English unit. So the compressor outlet, which is at 4000 psi, you can see temperature went from 80 degree Fahrenheit to 891 degree Fahrenheit, which when mixed, the mixture outlet is at 247 degree Fahrenheit. This is because the compressor, the mixture stream, the recycle stream is at much lower temperature. Because of that, this the mixture outlet is coming at the lower temperature. Okay, we can check the mass flow rate also. So as you can see, 5057 pound mole per hour. Since this is an English unit, it will be pound mole per hour. This much amount is being mixed with the only 3450 pound per hour feed. That's why the overall mixture temperature is lower, which is then heated to a 900 degree Fahrenheit, from where reaction is happening. Till this point we have complete vapor fraction only. After that, once we cool the stream, we have a vapor liquid stream from the outlet of heater, second cooler, like first cooler you can say, from where the flash is separating our main ammonia product, while the vapor product is being recycled back. Here one more thing we can look at is heat work required for the compressors as well as heater and reactor. Okay, these are the, again it's an English unit, so let's say rather than working in the English unit, we work in metric system, so that it's easier for us to implement it, like interpret the result. So I'm converting back to the metrics unit. Let's say for the B4 block, which is our exchanger block, this much calorie per second is our energy value. So I want to show this value in kilowatt. Let's change this option first. Heat work. Format. Yeah, I think it's converted. So B4 block, one three two three zero. No, it's not. Anyway, just keep in the mind that the exchanger duties. So here we have 643938 calorie per second as a duty of first heater. Our reaction is exothermic, which is generating heat. So you will see minus 316127. This much energy is being released. In cooler, we have to remove minus 879574. This much calorie per second energy. Okay. So clearly we can see we have one heat duty requirement and two cooling duty requirement, one for reactor and one for this cooler. So there is a possibility for us to do a heat exchange between this, to do a heat integration analysis, as has been asked in our question, that we have to do a heat integration analysis to save the net utility of the process, and how much energy we can save through this heat integration, that we have to find it. So let's say if we don't use any heat integration, that means we will require some hot stream, let's say some hot stream, like we are considering water. So some steam values at some medium pressure steam is there, and we are using it as a utility to heat up the feed mixture to the reactor. For the reactor we are using cooling water to cool down, to maintain the reactor temperature. Same for the cooler also, to remove this much energy we are using cooling water or some other coolant. So all this has a separate utility, which will add extra operating cost to our plant. But what we can do, we can connect this much energy, since we have energy being released from both reactor and second cooler, we can use that heat to provide energy into the first heater, right? So if you will see, the total energy output from reactor as well as cooler is summation of both. So we have 316127 plus 879574. So around 1195701 energy is being released, which is much surplus to this. So clearly there is a chance to do an heat integration or energy integration, where we can save overall utility of the plant as well as export some energy from the plant. So for that, what we will do, we will generate a steam, a low pressure steam, not low pressure, a medium pressure steam, let's say at 10 bar, from both cooler and the reactor. So for that, first let's add water as our another component in the mixture. So go to specification, add water as our another component, run the property analysis again. Since it's water, it will look for the binary data also, but we don't have to worry about it. It won't affect our main simulation. Okay. So now what we will do, we will add two exchangers, exchanger 1, exchanger 2. It's not showing labels. Just a minute. It's not showing energy labels. Yeah, they are back. Okay. So we will add two exchanger, exchanger 1, exchanger 2, and what we will do, we will share heat from reactor to exchanger as well as cooler to exchanger. Okay, so this shows that heat is being released and sent to the both exchanger 1 and 2 from reactor as well as cooler respectively. Now in the real world, it might not happen that you are transferring heat, rather it will be that column itself, reactor itself acts as a heat exchanger, where exothermicity of the reaction generates a steam. Okay, but right now we are treating it as a separate unit just for a learning perspective. Same way, we don't have to connect to heat exchangers. Rather, we can feed hot water on the other side of the cooler, which will take out the energy from our process stream and will generate a steam, low pressure stream. Okay, let's connect the material line. So we have feed 1, right? So this will become our water inlet 1, water inlet 2, and then S1, which is steam 1. Sorry, S1 is already present, so steam 1 and steam 2. Okay, now we have to provide the specification of W1 and W2, what will be the flow rate. So as of now we don't know how much water flow rate to be provided, so we will start with some guess value. Let's say we have hot water which is available at 80 degrees centigrade and 10 bar. So this is generally around the temperature pressure condition of medium pressure condensate which is present in the process plant. Okay, so pressure value will be somewhere around 10 to 15 bar. Okay, so I have taken is at 10 bar, and temperature value is 80 degrees centigrade. Okay, it could be higher than that also. You, for more accuracy, you can refer to any process plant data and take out the values from there. Let's say we start with a 1000 kilomole per hour flow rate for water 1, and since we have only water present here, molar fraction will be 1. Go next for water 2, again 80 degrees centigrade, 10 bar and 1000 kilomole per hour flow rate, and we will add mole fraction as 1. Okay, all the required inputs are complete. Pressure drop for both the new added heat exchanger, we will keep it as 0 and run the analysis. Okay, so results are generated. Here you can see let's look at the individual output result. So we have block 10 and 11, sorry, block 11 and 12. Block 11 we had water 2 coming and steam 2 forming. So what is happening? For a flow rate of 1000 kilomole per hour, temperature value is increasing to 179.977, but molar vapor fraction is 0.126 only. So we don't have complete steam generated. It's a mixture. It's a mixture of hot condensate and some steam, which is not desired. We want a complete conversion. Similarly, for B12 block also, if we see stream results, again molar vapor fraction is 0. So here only the temperature increase has happened. So that means that the flow rate that we have provided is much higher. So let's change it, and instead of 1000, let's provide 500 kilomole per hour flow rate for both W1 and W2. Okay. And run the simulation. Now what we see here, still not complete conversion has happened. So you can see 0.5 vapor fraction is generated here, while 0.02 fraction is generated here. That means again the flow rate is too much. So instead of 500, let's start with the lower value of 100 for both W1 and W2. And look at the results. So here we find vapor fraction as 1 and 1. But now what has happened? If you will look at the temperature value, here the temperature value is 254 degrees centigrade at 10 bar, which could be some reasonable value. But for the second heater, the temperature value is going till 2135 degrees centigrade, which is too high. That means we have some scope to change the W2 value. Instead of 100, maybe we can increase it to some higher value of, let's say, 200, and then see, since this much high temperature is not desirable and it's not possible anyway. Right now what we have done is we have just transferred the heat duty. But if you will, so that's why there are no pinch point analysis, or there are no temperature temperature profile calculation. But here the temperature is from 482 degrees centigrade to 27 degrees centigrade, and this side temperature value is going from 80 to 755. In that case, you can understand that there will be a crossover. So hot steam, its outlet will be much lower compared to the outlet of cold steam. So then this temperature crossover should not happen. Okay. So that point also we have to take into account. Right now we are not bothered about that. Right now we mainly want to look at the how much steam can be generated. Here for the reactor heat transfer, we are within the temperature limit, that the outlet of the reactor is 482 degrees centigrade and our steam is at 254 degrees centigrade, which is fine. But for the second heat exchanger, that is not the case. So again we have to vary the flow rate. So instead of 200, let's go at 250 kilomole per hour flow rate and see what is happening. So we have a steam, but temperature value is still high, 416 degrees centigrade. So that means there might be crossover happening. To avoid that, let's try to further increase the flow rate with 300 kilomole per hour and see the results. So we have 0.99, so almost one vapor fraction, like steam generation has been completed, like complete conversion of liquid to vapor has happened, and while the temperature is also below the outlet of the hot fluid, which is 274. Okay, so this is some acceptable amount. So here with this heat integration, what we have done, we have generated total of 100 plus 300, to total of 400 kilomole per hour steam at 10 bar and temperature value of 254 and 180 degrees centigrade. We can do further optimization to make both the temperature of steam 1 and steam 2 at same, and then we can mix it to some common header in a process plant. From there it can be used in the various utilities within the plant or outside the plant also. Right now this much steam we can utilize it to heat our feed mixture in our first heater. Okay, so that is also one possibility. Or instead we can borrow a steam from a steam header, and it could be high pressure steam, low pressure steam, depending upon what are the steam present in the plant, and our plant is able to generate 400 kilomole per hour 10 bar pressure steam, which can be supplied to a steam header. Okay, so that way there are process plant economics happening within the plant also as well as inter plant also. So in that you can save some cost for your plant. Okay, so that is nothing but the heat integration done within the ammonia process synthesis. Okay, I hope you have got the idea. So basically idea here was to how we can save the energy, since we have exothermic reaction happening as well as cooling requirement. We can generate the steam with the help of this exothermic outlet. That steam can be used within the plant or outside the plant also. So that was the case study 3 for today's class. Now we are almost close to end of the session. Yeah.
Yes, sir.
Yes, Rohit.
I am doubt in assignment number 11.
Yeah, okay. So for that I have already mentioned at the start of the class that for
Yes.
both assignment 9 and assignment 11, I have asked professor to look into that. So with the given data, no reaction is happening. I tried that
The
simulation
reactor
also. Sorry?
reactor data is not available in this case.
No, that I have uploaded in the Q&A forum, right? So if you will,
Yes.
my screen is shared, yeah. So if you will log into your Swayam portal, go to the course. So here you can see this Q&A tab. So if you will
Yes.
just go there. If you are not enrolled in this Google group, just join it. And then basically this group is not for me to discuss much, but this is for you guys to discuss in between yourself, and if there are any updates I post here. So I had updated this data, so it will load. Just a minute. Yeah. So these are the data for the reactor as well as the feed condition. Okay. But the another issue is that with the given data there is no reaction happening. That has been what other students are also complaining. So I tried that simulation with the given data. Again, no reaction was happening. So I have informed this to Professor Saha. Once he gets back to me, I will update it. Same goes for the assignment 9 that people had doubt in assignment 9. Again, for assignment 9, within the given data, what result we are getting and what answer has been provided are not matching. So for that also I have asked the professors. So once I get the response from him, I will update it here. I tried to post this information yesterday, but for some reason my messages were being deleted as soon as I was posting it. So you can see this message has been deleted. These are all my posts which I was informing the same thing, but I'm not sure why this was happening. So I had informed this at the start of the class also. Once I get any update, I will post it here in this discussion forum only. Okay?
Thank you, sir.
Yeah. Okay. Yeah, so it's almost end of the session. So yeah, I will stop it here. I had another 2 examples planned. One was of this reactor kinetics and another was of this LHHW kinetics, which is kind of related to your assignment 11. So maybe in the next class we can start off from here, and then I'm planning to do one assignment where we can do a big process plant simulation. So let's see if that data is ready on the class week 12 class. We can do that, or also I'm planning to do one extra interaction session. So in that my goal is to dedicate first hour for some problem solving session and second hour for revision of what we have done so far. So maybe at that time we can try to complete that problem. We will see. Okay.
In exam paper, which types of question are available?
So in the exam you won't be asked to do any simulation. So right now also in the assignment you have 2 kind of a question, right? The first step is that you have been provided some screenshot, and from that you have to interpret the answer, you have to give the answer. There are direct questions. Okay. And the second part B, is related to doing a simulation in Aspen Plus and then answering it. So since this exam will happen at multiple centers, there won't be Aspen Plus available. So most of the question, like all the questions, will be related to kind of a part A, where you have some information or some screenshots provided, and from there you have to give an answer to a different questions. Okay.
Okay.
Okay. So I will stop the recording. You can leave now.
Okay. Thank you, sir.